Hello, this is Commuting Local Hamiltonians Beyond 2D. I'm John Bastanja, and this is based on joint work with Youngwoo Huang. Our starting point, like many talks on quantum complexity theory, is going to be the local Hamiltonian problem. So in the local Hamiltonian problem, we're given a Hamiltonian H that acts on a system of n particles and can be written as a sum of local terms hi. We call hi local terms because they're only allowed to act on a constant number of particles. The local Hamiltonian problem is the problem of deciding whether the ground energy, or lowest eigenvalue of this Hamiltonian, is smaller than alpha or bigger than beta. Promise that one of the two is the case. Now, the local Hamiltonian problem is QMA complete, meaning that any efficient quantum verification algorithm can be reduced to the problem of checking the ground energy of a local Hamiltonian. And one way to think of the local Hamiltonian problem is kind of like a quantum analog of a constraint satisfaction problem. So that's a problem that's a family of problems that's known to be NP complete. But, we believe that the local Hamiltonian problem should be strictly harder than any constraint satisfaction problem because it's quantum. It's complete for the class QMA, and we think that QMA should be strictly bigger than NP. Why do we think this? Well, for one thing, so why do we think that the local Hamiltonian is a really, really quantum thing, and why does that matter? Well, for one thing, we believe that the ground states for these local Hamiltonians should be really, really complicated and highly entangled, and there should be no way to write these down classically, much less as like a solution to a constraint satisfaction problem. A second reason we believe this is because of the Heisenberg uncertainty principle, which says that you can't measure quantum information in two bases at the same time. This is basically encoded or captured by the fact that the local Hamiltonian terms don't have to commute with each other. And indeed, this non-commutation has been used in a lot of works doing reductions between local Hamiltonian problems to encode really complicated interactions in the low energy subspaces of local Hamiltonians. I think it's a really interesting question to try to understand what makes local Hamiltonian problems quantum. And a natural way to start tackling this is to remove some of these properties that we think make them quantum and see if they stay quantum or if they become classical. The commuting local Hamiltonian problem is exactly one of these, along this line. So it's very similar to the local Hamiltonian problem. The only difference is that we require that the local terms commute with each other. Enforcing commutation tends to make their interactions a lot simpler and easier to work with. So these commuting Hamiltonians are kind of a natural test bed for a lot of the biggest problems in quantum complexity theory and physics as well, quantum physics. So, and they also appear in a lot of places, in quantum computer science. So for example, almost all quantum error correcting codes are commuting local Hamiltonians and commuting Pauli local Hamiltonians. Recently, there was a construction of no low energy trivial state Hamiltonians, or NLTS Hamiltonians, that used good codes, so commuting local Hamiltonians. And there's been a lot of work on the thermal properties of ground states of commuting, or lower energy states of commuting Hamiltonians, and like Gibbs sampling of commuting local Hamiltonians. So these objects appear in a lot of places in the literature, but the problem that we are focused on today is understanding the complexity of the commuting local Hamiltonian problem, or the CLH problem, which is deciding whether or not the ground energy of these objects is high or low. Now, in our case, there is actually a simplification we can make. It's known that the commuting local Hamiltonian problem is equivalent to the commuting projector local Hamiltonian problems, where each of the hi's squares to itself. And for this instance, the spectrum, or the lowest eigenvalue, will be an integer. So just keep that in mind. So the commuting local Hamiltonian problem, like I said, is a kind of less quantum version of the local Hamiltonian problem, and we might worry that it's so less quantum that it's actually classically possible to verify the ground energies. And indeed, there's been a long line of work showing that ever increasingly expressive families of commuting local Hamiltonians are contained in NP. So Bravi and Viali started this line of work by showing that the two-local commuting local Hamiltonian problem, so this is where local terms commute and only act on two particles, but the particles can be arbitrary qubits, they can have arbitrary dimension, or polynomial dimension, sorry, is in NP. Harnov and Eldar extended this result to three local terms, where each particle was promised to be a qubit, or qtrits, if they were also promised that the interaction graph was nearly Euclidean. Going beyond three local, the works of Shuk and later of Aharonov, Kenneth, and Vigdorovich showed that if you restricted your local Hamiltonian to be 2D geometrically local and on qubits, you again can show that the verifying the ground energy remains in NP. Finally, recently, Irani and Zhang showed that Q-trit local Hamiltonians on a square lattice are also in NP. That's the current boundary of what we know before this work. So I'm going to get into explaining what we've done. But before I can explain what we've done, I have to highlight our main caveat. So we introduce a new restriction on commuting local Hamiltonians, and it buys us a lot in other ways. But this restriction is called the rank 1 restriction. So rank 1 local Hamiltonian term is just a projector onto a rank 1 state. So it's just projecting onto that state locally. So you might notice that it's technically going to be identity on the particles where it doesn't act on. But we call a local term rank 1 if it can be written as a rank 1 projector on its domain. There are some pretty common examples of these. So for example, the 3-sat or any sat instance is a rank 1 local Hamiltonian problem. You can think of the term, for example, x1 or x2 or x3 as a projector onto all zeros, because that's the only configuration of the variables that would not satisfy that clause. So it's the only vector that's penalized. Similarly, people study the Heisenberg local Hamiltonian a lot, which is a two-local Hamiltonian where you put EPR pair projectors onto every edge in a graph. And this is also known to be QMA complete. To say more on this, both of these, 3-sat and Heisenberg local Hamiltonian are complete for their respective classes, but it is not known whether rank 1 commuting local Hamiltonians are equivalent to the general commuting local Hamiltonian problem. So with this restriction in mind, I'm going to state our results. So the first result is that 2D geometrically local commuting local Hamiltonians, where the terms are rank 1, but the particles can be arbitrary polynomial qubit dimension, is contained in NP. And similarly, we can show that 3D geometrically local commuting local Hamiltonians on a cubic lattice with the same restriction, so any qubit dimension, but rank 1 terms, is also in NP. And finally, I'll just comment that for people who work on the commuting local Hamiltonian problem, an interesting property is whether or not the reduction is so-called constructive, or if it implies that there's actually a classical description for the ground states of these local Hamiltonians. So I'll just say that in contrast to the recent slate of works, which have constructive reductions, our proofs are not constructive. So it's not clear whether or not the ground states of these Hamiltonians are actually classically describable. In the rest of the talk, I'm going to try to explain how to put these commuting local Hamiltonian problems in NP. And to start, we're going to need to know the main tool that a lot of these commuting local Hamiltonian papers use, which is called the structure lemma. The structure lemma tells us exactly how a pair of Hamiltonian terms are allowed to commute with each other. And it basically says that if you have two Hamiltonians, h1 and h2, and they commute, then they have to both block diagonalize, and within each of the blocks, they have to look like a product. So here we see that we can block diagonalize both these projectors, and within each block, they act on different parts of a two-particle system. We can see how to apply this briefly to the two-local case, which is the original case that Bravi and Viali considered. So in this case, we can just focus on a pair of terms, and they're both two-local. And using the structure lemma, we can write that middle qubit, qdit, in terms of the block diagonalization of P1 and P2. So we can write this entire system as a direct sum over all of these little blocks. That should be P1 there, not P3, sorry. And within each of the blocks, that middle qdit looks like a pair of qdits, and the two projectors don't touch. So by telling us a choice of pi I where the ground state is going to live in, we can just like focus on that one block of the block diagonalization, and within that block we can basically have removed one edge in the interaction graph. So we've like split one of these qdits and removed an interaction between a pair of terms. And if we repeat this for all pairs of terms, then what we'll end up with is a bunch of like isolated, like, like the projectors just act on two particles and don't interact with any other local terms, and we can just solve that classically without even needing a proof. When we try to take this beyond two local, we run into a really interesting problem, which is that the structure lemma, it really only holds for a particular pair of Hamiltonian terms. So if we have a really complicated interaction graph where like multiple things are overlapping on multiple particles, then taking the decomposition, the block decomposition for one pair of local terms is not going to be consistent with another local term. So it's really not clear how to extend this strategy to more than two local interactions, but this is the work of Aharonov and Eldar. I'm not going to get into that. Instead, I'm going to take a little tangent and talk about the work of Aharonov, Kenneth, and Vigdorovich, who give another like meta strategy for proving containment in NP of commuting local Hamiltonian problems. So they consider the case of 2D geometrically local Hamiltonians. It'll be easier to draw a grid. And they consider the following thought experiment. Imagine that I could start with a grid and puncture holes so I could remove some of the local Hamiltonian terms. Then what I would most naturally like to do is simply draw lines, like a triangulation, between all the holes and group all the qubits that are inside of the group all the particles that are inside of the triangulated cells into a single megaqudit, sorry. And because I punctured all the holes, the only place where a Hamiltonian term could touch three of these sites simultaneously would be if the Hamiltonian term touched a vertex. But because I know that all the vertices of the triangulation go through the holes, I know that if I group all the remaining Hamiltonian terms, everything becomes two local. So now I've basically reduced to a two local Hamiltonian and can apply the result of Bravi and Vialli to show that this is in NP. This is basically our high-level goal, but we're going to show that there's a very different strategy for doing this puncturing. So let's first see what happens when we just blindly apply the structure lemma to rank 1 local Hamiltonians. So if we have two projectors, P1 and P2, and they're both rank 1, so they're projectors onto psi 1 and psi 2, it turns out that they have a very simple decomposition when we apply the structural lemma. There's exactly two cases. Reducing case and a singular case. In the reducing case, the overlap between the two states, psi 1 and psi 2, is 0, so the two states have to be orthogonal. And if we look at what that means for the middle qdit, it means that we can basically block diagonalize that qdit so that each of the projectors is projecting onto an orthogonal subspace, or is acting within an orthogonal subspace. Similar to the Bravi-Vialli thing, the prover might hope to tell us which of the two subspaces the actual ground state lives in, which means that we can disregard one of the two terms. The other case is what we call the singular case. So the only other way that two rank 1 local Hamiltonian terms can commute is if they have the exact same state on the middle section and they're in tensor product. This case is even easier because they basically, within the middle section, they only penalize a single state. So we can just like remove that subspace and delete both these terms because they'll never trigger. And remember I said that for the case of a square lattice, for example, like the spectrum will be integer, and because we're removing two terms, we can't improve on that. So in the case of a square lattice, it's really easy to just say to deal with the singular case. If we again focus on the square lattice, because that'll be the most instructive for us, we can look at a single qubit and the 4 terms that surround it. Now, the most interesting case, as I said before, is going to be the case when everything is reducing, so both the pairs are reducing. And the whole point of looking at the square lattice, or anything with 2D geometric locality, is that things like every projector only has 2 other terms that it interacts with on more than one particle. So for example, P1 only interacts with a single particle with P2. But with Q1 and Q2, it has a bit more complicated interactions. It interacts on 2 particles. But the point is we can consider the pair P1, P2 together and Q1 and Q2 together, and they both only overlap on that central qubit. The interesting case, or the most interesting case for our problem, is when both pairs commute in the reducing way. So remember, this means that they act on orthogonal subspaces within that middle qubit. So we could imagine that the prover sends us a projector, pi sub p, that will kill one of P1 and P2. Let's say it kills P2. And then they send us another projector, pi q, that kills one of Q1 and Q2. So let's say it kills Q2. Okay? Now, we would be left basically having removed these 2 terms, and this would be a successful puncturing of our Hamiltonian. But the problem, like I said before, is that the projector pi q might not commute with P1, and the projector pi p might not commute with Q1. So the final step, and the main step, is showing that we can take this information from the prover and round back to a commuting local Hamiltonian in a way that preserves the completeness and soundness of the original commuting local Hamiltonian problem. Okay, so like I said, after doing this puncturing, we're left with a ground space that lives in the intersection of these 2 projectors. So I've just negated the conjugate. So I've just negated the thing. So originally I would have started with p and then sandwiched it by pi q, and now I'm just taking the negation of that subspace, which is pi q minus pi q p pi q, and similarly for q. And the idea for rounding is really quite simple. We're just going to take the projection onto the greater than 0 subspace of the product. So we'll take a singular value decomposition of p tilde and q tilde, and then just take the projector onto the greater than 0 subspace of that. It's not hard to verify that this commutes with every other Hamiltonian term, because the only place we modified p and q at was that single site in the middle, and nothing else in the local Hamiltonian problem interacted with that middle particle. Showing that this reduction preserves the completeness and soundness is a bit more challenging, and basically uses Jordan's lemma to characterize the singular value subspaces. In this case, we only have 2 non-commuting guys, so we can break them down into pairs, into subspaces that have a pair of vectors. And for some context, the original Aharonov, Kenneth, and Vigdorovich result, used the 2D geometry to show that you could puncture a local Hamiltonian by inducing a toric code-like error, and then correct that error because it looks like a string. So this technique really fares poorly in 3D because the sort of natural equivalent of the toric code can have plane-like errors, or errors that slice through the entire plane. So it just doesn't seem to work as nicely. But in our rounding scheme, the rounding doesn't induce errors that look like corrections to a toric code. It's more local, so that the kind of errors we get are just between the remaining things touching a single site. So this is way more flexible and allows us to actually start tackling these 3D geometries. In 3D, we have to now, instead of puncturing at a single point, you have to actually puncture an entire line through a local Hamiltonian. So, just to summarize what we've done so far, we've taken one of these little plaquette terms, so like these the 4 terms that interact on a single particle, and we removed 2 of them, and we're able to round the remaining 2 back into a single Hamiltonian term and effectively puncture the Hamiltonian. In 3D, like I said, we can just repeat this a bunch of times to produce an entire line. And instead of triangulating, like, connecting the holes with triangles, we have to, like, what we call cubulate, or like put a cubic lattice interposed onto the original 3D lattice, such that the edges of the cubic lattice go through the lines that we punctured. Okay, things are a bit more complicated in a 3D case because of what we call blockages, or times when you can't actually continue puncturing the line, but it turns out there are some techniques for dealing with that. So yeah, if you wanted to apply this to 4D, for example, or higher dimensions, you would quickly start to run into the following problem, which is that every time we have to puncture our Hamiltonian and round it, we end up producing Hamiltonian terms that are more local than they started with. So if you have to, like, repuncture next to an already rounded term, you'll just end up growing the size of that term. The nice thing about the line, or the 3D case when you're puncturing lines, is you only have to puncture next to a hole. So you never actually have to re-round an already rounded term, and so things stay relatively local. But in 4D, if you wanted to apply this high-level meta strategy, you would have to puncture out an entire plane, or like a plane like a surface in your 4D grid, so you could, like, hypercubulate or whatever the space. So that's where that's why we're not able to go past 3D, and we're just stuck with 3D. Yeah. So to conclude the talk, let me just talk about some of the next steps. So, in our work, we crucially used this rank 1 restriction, because it allowed us to get a better handle for the ways in which adjacent terms can commute with the structure lemma. But these rank 1 commuting local Hamiltonians are not known to be complete for the CLH problem. It would be nice to get some evidence either way. So if they turn out to be complete, then that'd be super interesting, because it means we have shown that a large family of these commuting local Hamiltonian problems are actually easy, and it would give me a lot of hope that one could show the entire commuting local Hamiltonian problem with arbitrary qubit dimension and locality would also be contained in NP. I kind of believe that the rank 1 restriction is quite strong, so it would be interesting to see if you could reason about why the commuting local Hamiltonian should be harder than NP. Secondly, we introduced a new tool for rounding local Hamiltonians, which was this idea of using Jordan's lemma and the singular value decompositions to analyze pairs of non-commuting terms and round them back to being commuting. Unfortunately, there's really not a lot of tools for analyzing commuting Hamiltonians, and there's probably even fewer tools for analyzing regular local Hamiltonians, and a lot of them so it would be really nice to find more tools. I think that's probably one of the biggest open directions in quantum complexity theory, but for the commuting case, you might hope that you can find simpler tools. This brings me to the third point, which is just to say that a lot of the tools that we do have for commuting Hamiltonians and local Hamiltonians are very linear algebraic and mathy. So for example, the main tool for understanding local Hamiltonians has been these perturbative gadgets, which use complicated Schrafer-Wolff transforms to encode information into these low energy subspaces. And again, in the commuting case, the structure lemma and our new Jordan's lemma approach are all very linear algebraic. Classically, all the reductions are super nice and just involve applying gadgets. So I think it's a huge, I would love if there were more gadget-like reductions for local Hamiltonian problems. Okay, thank you so much for listening to my talk.